Okay, so I am now glad that I did create the Google Classroom, since I assume you are now all aware that we have 3 more weeks off, at least. And the next day we may come back to school is now May 4th, which is crazy. It sucks, and I wish this didn't happen on my first year teaching calculus. But that is where we will, when we start just doing review, we will use both Google Classroom and AP Classroom for that. Google Classroom is where I will post lots of different review things and response questions for you to work on, and then that I will go over on videos as well. One thing I want to show you real quick before we get into today's lesson, I'm going to share my screen. Okay, so when you are at Google Classroom, you scroll down a little bit. The second thing I ever posted on here, this YouTube link, as I said, here's the Advanced Placement Calc BC YouTube channel. If you click that, it is going to take you to all the Calculus BC review session videos that they are doing. They started off with 3 from Unit 9. I know Unit 9 is not on the exam, but they covered a bunch of topics that are still on the exam within those topics. Because within Unit 9, we did do a lot of differentiation and integration, function analysis, particle motion, that kind of stuff. So they made sure to cover that kind of thing as well. And then they have started some videos on the unit we are now covering. And then next week, they'll do some Taylor polynomials. Then for the 3 weeks that we now are no longer in school, they're going to do review videos. This is extremely helpful. These guys are very good calculus teachers doing these videos. Then also at the Google Classroom, the thing I most recently posted, this assignment. Again, due dates are just vague. They mean almost nothing, but I did still put a due date on this so that you have some idea of when it would be a good idea to finish it. It's essentially just a giant review sheet of every definition, theorem, and rule we have covered throughout the entire year, starting with limits up through what we are doing now. If you want to not do Unit 9 when you're doing it, that is fine and reasonable, since it's not on the AP exam. And I will post other stuff here as well as time goes on. We'll use Google Classroom and AP Classroom. Any questions before we go into today's lesson? We will continue where we left off on alternating series, and then go on to section 22, ratio and root test.
Number 7 on page 106, the comparison homework.
Number 7, page 106, comparison. Let me find that real quick. What about it?
What are you supposed to compare it to? That's like a really weird series.
Okay, so what they compared it to was n to the 3 halves.
Like why?
The reason for that is, yeah, I'll write out the problem and show you. We're doing page 106, number 7, with sum from n equals 1 to infinity, square root of n over n squared minus cosine squared. Okay, I'll share my screen and so if we ignore the cosine squared n part, if we ignore that part, then we have square root of n over n squared. And well, square root of n is n to the 1/2. So we have n to the 1/2 over n squared. And that is, well, how would we simplify this? When we divide exponential terms, the exponents subtract. So we have 1/2 minus 2, which is what?
Negative 3/2.
Negative 3/2 or negative 1.5. So really, this is just n to the negative 3/2, as you just said. So that's what this summation is when you ignore the minus cosine squared n in the bottom. So I was wrong when I just quickly looked at their key. I should have said negative 3/2 or 1 over n to the 3/2.
Oh, okay.
So this right here is what they are comparing it to. They're comparing it to something that looks very similar to it, getting rid of something that is very complicated. The cosine squared n here causes it to be rather complicated. We eliminate that, and that's what we're going to compare it to. And so then if we go throughout those steps, we're just going to do limit comparison test, limit as n approaches infinity of, okay, this one would be the first one. I'm going to call that my a sub n. This will be b sub n. So square root of n over n squared minus cosine squared n all over 1 over n to the 3/2. Limit is an approach to infinity of a sub n over b sub n. That's the limit comparison test. Well, if we flip and multiply this, that's the limit as n approaches infinity of square root of n over n squared minus cosine squared n times n to the 3/2. And that's limit as n approaches infinity. Okay, well, n to the 1/2 times n to the 3/2 is what?
N squared.
Squared.
N squared. Oh yeah, duh, sorry. I was being dumb there. Yes. Wait, no. Yeah, you're right. N squared on top over n squared minus cosine squared n on bottom. And as we go off towards positive infinity, what is this going to approach? What's the biggest or smallest cosine? What's the biggest or smallest cosine squared of n is ever going to be?
It's going to be -1 or 1, right?
Yeah. The smallest cosine squared will ever be is -1. The biggest it will ever be is +1. So that means that in the denominator, we're only, at most, we're only ever adding +1 or -1 to this denominator n squared, which would be almost negligible, which would be not doing much to the entire term as we go off towards positive infinity. As we get close to like 1,000,000, that'd be 1,000,000 squared over 1,000,000 squared minus 1, maybe. Well, so then that limit would then be a +1. Yeah. Any other questions before we go on to today's lesson?
Number 11.
Same page?
Yeah.
Nice. Okay. 1 second. Okay. Number 11. We have the sum from n equals 1 to infinity of 4 to the n over 3n to the fourth. Okay, one thing to quickly make note of that I didn't really mention on this first problem is that in limit comparison tests, it's that if the limit of a sub n over b sub n equals a positive finite value, then they will do the same thing. They will either both converge or both diverge. And the reason this one, we compared it to 1 over n to the 3/2. And wait. Oh, that is greater than 1. Duh. N to the 1 over n to the 3/2 is a convergent p series because this p 3/2 is bigger than 1. And so that's why then the one we were asked about, a sub n, would also converge since b sub n converges and the limit is a positive finite value. On number 11, I'm sorry, right now I don't understand why it's divergent. I'm going to look that up and get back to you on that.
Yeah, like when I was, is it just because if they're comparing, they're using 4 to the n over n to the 4th power, each of those individual components are divergent. So is that why it's okay to use this? Like, when do we know when we can do this to cancel out terms of the original problem?
Well, I wouldn't use limit comparison test for that one. We're going to talk about ratio test today, and ratio test would make that one way easier. And
Okay.
ratio test would make it more clear to me that it would be divergent. Because we have not talked about, so in the key, they used n to the 4th over 4 to the n. No, they didn't. They just took off the 3. In the key, they used 4 to the n over n to the 4th as their comparison one, because all they really did was just drop the 3, and then the limit would end up being either 1/3 or 3, depending on whichever one you put on top of the other. But we currently don't even have a good reason for why this one is divergent. And since we, sorry, let me show this one. We don't currently have a good reason for why this one is divergent, b 4 to the n over n to the 4th. I mean, both 1 over n to the 4th would be a convergent p series because that power is bigger than 1. But 4 to the n would be divergent. So there's not a good reason for why this is divergent. At least I don't currently have a good reason for you on that. So this particular problem would make better sense by doing the ratio test, which we will learn later today.
Okay.
But this one, according to their key, is divergent. And when you do a limit comparison test, the limit does end up being either 1/3 or 3, depending on how you put the sequences, whichever one's on top. There's not a good reason for why this one's divergent. And so I would use a different test. But it was in that section, so. Okay. Let's go on to today's stuff. Alternating series. So on Monday, we started doing alternating series. And we talked about an alternating series is one that's going to alternate signs. It's going to alternate signs like -1, -3, 1/3, +1/9, -1/27, and so on. And every alternating series could be written as -1 to the n power or -1 to the n plus 1, something like that. That's what makes it alternate signs. And then times its sequence. An alternating series will converge if it passes the nth term test, meaning where the limit as n approaches infinity does equal 0, and where eventually it is consecutively decreasing, where every consecutive number is less than the previous number. If both those things are happening, then it will converge. And you would need to show that both those things are happening before you can say that it is converging. Then we looked at this first example, and it's the alternating harmonic series because it is, if we ignore the negatives, it's a harmonic series, 1, 1/2, 1/3, 1/4, and so on. So it can be written as -1 to the nth power times 1 over n, so just sum of 1 over n is the harmonic series. We need to look at these two questions when we're figuring out whether it's convergent with alternating series. The limit is n approaches infinity of 1 over n. That's doing the nth term test with the sequence, and this one does equal 0. And each consecutive term would be less than the previous term, and 1/5 is less than 1/4, 1/100th is less than 1/99th, and so on. So it is decreasing, and since both of those things are happening, it will converge by alternating series test. Okay, let's look at number 2. On number 2, this one is also an alternating series because we have -1 to some n power. This one has n plus 1 power, which is going to mean it's going to be the even terms being negative. And let's write a few of those to see what's really happening. So when n is 1, that would mean -1 to the 1 plus 1 power, so -1 squared. So that's going to be positive. So our first term is positive. Times the 1. We just have a 1 on top. Then on the bottom, we have 2 times 1 minus 1. So we just have a 1 on bottom. Then if we plug in 2, that'd be -1 to the 2 plus 1, so -1 cubed. So it's going to be negative times the 2 over 2 times 2 minus 1 is 3. And it's just going to continue alternating signs now. So next is going to be plus. We're plugging in 3, so that'll be a 3 on top over 2 times 3 minus 1 is 5. And then minus, now it's going to be a 4 on top. 2 times 4 minus 1 is 7. ... Okay, so is term n plus 1 less than term n? Meaning, is each term less than its previous term? If I picked some random term, would it be less than the term right before it if we ignore the negatives.
Yes.
Yeah, that definitely would be happening since it is bottom heavy. So that would be a yes, it is decreasing. We also need to check the nth term test, actually write this out. So the limit is n approaches infinity of n over 2n minus 1. Well, that is 1/2. Ooh, both of these things have to happen for it to be converging. So it is decreasing over and over and over again. But the limit is not 0. Since the limit is not 0 and the limit is 1/2, it will be divergent. It's going to diverge by alternating series test. Okay, on letter A. We again have an alternating series because of the n plus 1. It's going to be the even terms that are negative. We have n plus 2 over n. Well, let's check the nth term test of the sequence. So we want to check, does the limit as n approaches infinity of n plus 2 over n, we need that to equal 0 so that this will converge. What does that limit equal?
1.
Yep, it equals 1. Okay, so we already see it diverges by nth term test. And we can do the same thing to this one. We want to see if it passes the nth term test. So the limit as n approaches infinity of square root of n over cube root of n. We want that to equal 0. But what do we have going on here? We have limit as n approaches infinity of, well, that's n to the 1/2 over n to the 1/3. Well, when we're dividing exponential terms, we want to subtract the exponents. So what's 1/2 minus 1/3?
1/6.
1/6. And so we have limit as n approaches infinity of n to the 1/6 power. Well, that will go to positive infinity. So it diverges by nth term test. Okay, and I'm going to skip letter C for now. Next. Okay, this example 4 and this paragraph is talking about finding the error in the summation and doing an approximation of what the summation might actually be. You can ignore the first sentence. We haven't talked about Taylor polynomials yet. We'll start talking about those on maybe Friday, definitely next week. And we're not even going to do Lagrange remainder. It's difficult and not on the AP exam. Okay, but when doing remainders, when finding the remainders, where in these series, it's a lot easier than what we'll do later on. When they alternate, it's way easier. So since the terms of the series get progressively smaller, the error in an approximate value of the series using n many terms is just going to be the n plus 1 term. So if we use n many terms, the error between that approximation and the actual sum is just the next term in the sequence, which is pretty easy to deal with. And if I'll rewrite that slightly differently, maybe it'll make a little more sense. What that means is that the the actual sum of all terms is, okay, S sub n represents a partial sum. It represents a sum of n many terms. So the actual sum of all terms is going to be between, I should have said the word between, S sub n minus the error, using a capital E for error, and S sub n plus the error. And because of that, we can figure out what the error is. They just told us that here, that the some approximate value for the series is just going to be the n plus 1 term. I mean, the error in the approximate and the actual is the next term. And so if we do that here, we're asked to find the range of the sum for this. So this is an alternating series because we have -1 to the n plus 1 power over n factorial. And we're asked to use the first 5 terms. If we start writing it out, this summation would equal, well, if we plug in 1, that'd be -1 to the 1 plus 1, which is 2. So -1 squared over 1 factorial. So that's just a 1. Then plugging in a 2, we'd have -1 cubed over 2 factorial. So that's going to be -1/2. Then it's going to be plus plugging in 3, 1 over 3 factorial. Well, 3 factorial would mean 3 times 2 times 1, so 6. And then minus 1 over 4 factorial. Well, 4 factorial is only 4 times 3 times 2 times 1. Or just taking 3 factorial and multiplying by 4. So 4 factorial is 24. And then plus 1 over 120. And it would keep going if we wanted the entire sum. So what we're going to do is, let's actually first show that this is convergent. So does this pass the nth term test? Limit as n approaches infinity of 1 over n factorial. What would that limit equal?
0.
Yes, it would equal 0. And a sub n is continuously decreasing. So convergent by alternating series test. Okay, so we have shown it is convergent. It will converge to some value, and we're going to get a very close approximation of what that value is. And so, as we set up here, the actual sum is going to be somewhere between S sub n minus the error and S sub n plus the error. And we're told here that the error in approximating an n amount of terms is just the n plus first term. So the error will just be here. The error is going to be a sub 6. Because we're asked to use the first 5 terms. So that means that we're only going to sum up the first 5 terms, and we're going to use that as an approximation for what our actual sum would be. And in an alternating series, the very next term is just the error in our approximation and the actual value. By a sub 6, I'm meaning the 6th term in the sequence. So let's figure out what S sub 5 is. Can't see that. There we go. S sub 5, that represents the sum of the first 5 terms. So I'd just be taking these 5 terms and adding them all together. 1 minus 1/2 plus 1/6 minus 1/24 plus 1 over 120. And if you were ever asked to do this, you definitely would be allowed a calculator. And if I add all 5 of those up in my calculator, I would get 0.633333333. It just repeats threes forever from then on. Okay, so that is the summation of the first 5 terms. And so the actual sum is going to be somewhere between S sub n minus the error and S sub n plus the error. Well, what is our error? Well, the error is just going to be the very next term, which is a sub 6. Well, a sub 6 is just going to be, well, now it's going to have to be negative, so negative 1 over, I'll just put 6 factorial. 6 factorial is 720, so you could just write 720. But so the error is just the 6th term, which would here be negative 1 over 6 factorial, or negative 1 over 720. We can get the decimal for that. That decimal, did I write that anywhere? I did not write that down, so I'm gonna figure out what that is now. Okay, negative 1 over 720. Okay, that is about negative 1.001389. So that is the error, meaning the actual sum is going to be somewhere between the summation of the first 5 terms plus the error and the summation of the first 5 terms minus the error. And when we do that, our actual sum, which I'll rewrite that to you, which is negative 1 to the n plus 1 over n factorial. And our sum is going to be less than the first 5 terms added together plus the error, and then minus the error, which would be about 0.634722.
Mr. Hunter,
Yeah.
how'd you get the negative 1.001389?
I just typed in my calculator negative 1 divided by 720.
I got something different. I don't know if I did this right. I got negative 0.001388.
Yeah, that's what I had.
Negative what?
Negative 0.00138.
So just not the 1?
Just not the 1.
Yeah.
Oh, I just read my calculator wrong. Oops. Yeah, you're right. This should not be a 1 there.
Okay.
Yeah, you're right. But this down here, this is the final right answer. If we now take the 0.63 repeating and add that error, we get 0.634722. And then if we subtract it, we get 0.6319444. And so the actual sum would be somewhere between that, which is still, it's a very accurate summation there, very close.
In the middle of that, is that just S equals and then you wrote the summation again?
Yeah, I did. Just so you understood what my capital S represented. And so I was about to not put that, but then I wanted it to be clear what I was talking about. That the actual summation that we were dealing with, it does converge, which we showed earlier, and that actual summation, which I have it equal to just a capital S, is somewhere between these two values. The partial sum of 5 terms plus the error and the partial sum of 5 terms minus the error.
How do you decide which term is your error again?
You would usually be told. You would be told what to use for your partial sum.
Oh, okay.
The error is just the next term in the sequence.
Oh, okay.
So we were told to use 5 terms. So our partial sum was going to be S sub 5, the summation of the first 5 terms. And then the error is just the next term in the sequence. So the error was just the 6th term in the sequence. Okay, well, let's go on. Okay. On the next page, you can skip the top paragraph. This then talks about absolute and conditional convergence. And we are told that a series will be absolutely convergent, or it will have absolute convergence if both the summation of the absolute value of the sequence and without the absolute value converge. So if it converges with the absolute value and without the absolute value, it's absolutely convergent. And so it will usually be easy to see that the sum of the absolute value converges. And then if that's happening, that would also most likely also happen. A series is only conditionally convergent if the alternating series without the absolute value converges, but the series with the absolute value does not converge. And we'll show both.
So this is for alternating series only.
Yes, this is still for alternating series only. Because putting on the absolute value then eliminates the negatives, and essentially we're just looking at the summation of the sequence without the -1 to the power. And so it will be absolutely convergent if the alternating series already converges normally, as well as if it converges without the negatives, because essentially the absolute value sign just gets rid of negatives. So if it converges by alternating series test and converges because of the negatives, without the negatives, then it would be absolutely convergent. If it does not converge without the negatives and only converges by alternating series test, that's only conditionally convergent. And so looking at these, we're going to look to see whether it's conditionally convergent, converges absolutely, or diverges. So actually, I'm going to skip A for now. Feel free to do it on your own, but I want to save time. So on B, well, we're going to continue to have an 8 on top. It's just going to go back and forth between negative and positive. Starting at 0, -1 to the 0 power, that's just going to be a +1. Anything to 0 power is 1. So it's starting off with positive 8 over. Well, that will end up being just 1 on bottom. Then -8 over square root of 2 plus 8 over square root of 3 minus 8 over square root of 4, and so on. Okay. Well, this does pass the nth term test, because if we take the limit as n approaches infinity of 8 over square root of n plus 1, well, that is clearly bottom heavy. The only thing on top is the number 8, so that limit is 0. So it passes the nth term test and is decreasing. So converges by alternating series test. So it does converge by the alternating series test. So looking back up here, we see here the sum of a sub n does converge. We just now showed that. The sum of a sub n does converge. Now we want to see if we throw the absolute value sign on there, does it still converge? If we throw the absolute value sign on there, does it still converge? And if it still converges with the absolute value sign, meaning without the negatives, then it would be absolute convergent. If it does not converge with the absolute value sign, then it's only conditionally. Okay, so what we're going to do is we'll do the limit comparison test. And so what I mean is we're now throwing absolute values on there. We are wanting to now see, does the summation of the absolute value of -1 to the n of 8 over square root of n plus 1, does that converge? And doing that essentially just gets rid of the -1 to the n power. So we have 8 over square root of n plus 1. We're going to do the limit comparison test. And I want to compare it to one that I know something about and that looks similar to this, but just slightly different, slightly less complicated. And so what we're going to compare it to, is n approaches infinity of, I'm going to compare it to 8 over just square root of n. Just get rid of the plus 1 there. Well, the summation of 8 over square root of n, is this convergent or divergent?
Convergent.
Well, this right now is the summation of 8 over n to the 1/2 power. So this is a p series, and our p power is 1/2. If our power is less than 1, does it converge or diverge?
Divergent.
Yeah, this one is divergent. Okay, so we're going to compare it to a divergent p series, which would mean the limit as n approaches infinity of 8 over square root of n plus 1. Okay, do I need to put the giant fraction over fraction again? When I divide by this fraction, what's going to happen to that fraction?
Flip and multiply.
It's going to flip and multiply. So now I'm just going to have square root of n over 8 like that. When I flip and multiply my bottom fraction, and 8s would cancel. We have limit as n approaches infinity of square root of n over square root of n plus 1. That limit is a positive 1. So that means, by limit comparison test, that they will do the same thing, and the same thing that we are comparing it to diverges, meaning this one also diverges. So sum of the absolute value of -1 to the n times 8 over square root of n plus 1 diverges, meaning the one we are asked about is only conditionally convergent. So if it converges by the alternating series test, but with the absolute value sign diverges, then it's only conditionally convergent.
Should the limit comparison test be our go-to for the finding out if it's conditional or not?
That just depends on the form that it's in. Limit comparison test is by far easier than the direct comparison test. So if it's not a geometric series or a p series or telescoping or alternating, and with the absolute value, then it's not alternating anymore. So really, technically, I should have had the absolute value sign still there. With the absolute value sign, it's not alternating anymore, so we can't perfectly look at that rule. And so it's not in one of those other forms. And so out of the other tests we've learned so far, limit comparison test is the easiest one to use. And I want to get to ratio test today because that is the easiest test to use. Okay, if we look at this one here, this test, this one, limit as n approaches infinity, we'll go up, of, well, we have -1 to the n squared over n divided by 2 power. Well, that's just going to still have it alternating. Let me show. So if we plug 1 in, you'd have 1 plus 1 would, over 2. Well, 1 put 2 over 2, that's 1. So then that's going to first one be negative, so negative 1/2. If you then plug in 2, 2 squared plus 2, that's then going to be 3. So the top will be negative again over 2 squared, which is 4. But the next one is going to be positive. And then the one after that's going to be positive, and then negative and negative, positive, positive. So it is alternating, but it's just a little weird. And then that would be 8, and then 16, and so on. Well, this one, if we now do the limit, well, that top thing is just the making a negative, positive thing. So we really just have limit as an approach infinity of 1 over 2 to the n. Well, that right there is a is going to go to 0 and is decreasing. So converges by alternating series test. Now I want to check to see if it also converges with the absolute value sign. Limit is it from n equals 1 to infinity with the absolute value of negative 1 to the n squared plus n over 2, all over 2 to the n. Well, when you do absolute value of that, that's just making all that go away, because it's just essentially undoing the negatives. So it's really just summation of 1 over 2 to the n. Well, that right there, that's just a convergent geometric series. This is just a convergent geometric series. Converges by geometric series test with r equals 1/2. And so, since it converges with and without the absolute value sign, it is absolutely convergent. Okay. And then I'm going to skip number 6 as well, going on to the ratio test. Ratio test. Easiest test to use. So the ratio test is also very handy for when we're dealing with stuff like this, when we're in factorial or anything with factorials. This is the preferred test. Because we can see by the nth term test that this one would approach 0, so it could converge. But there's nothing really else we can do with that. It's not a normal function that we deal with. So this fixes a lot of the difficult ones. And then the easier series, they also have their own tests. Okay, so actually, what does the ratio test say? So the ratio test is essentially just comparing the nth term to the n plus first term. It's comparing two consecutive terms as we far down the line. So given some series, sum of a sub n, we're going to let the capital L be the limit as an approach infinity of the absolute value of a sub n plus 1 over a sub n. So here it does matter the order. When we did limit comparison test, it didn't matter which one, what thing was on top. When you do some stuff, it doesn't matter what thing's on top, but here, a sub n plus 1 goes over a sub n. So the limit is an approach infinity of that absolute value. So you're just finding that limit. And if that limit is less than 1, it will be absolutely convergent. And if that limit is greater than 1, it is divergent. If that limit equals 1, it is inconclusive and doesn't tell us anything. So let's look at that basic one. We want to decide, does the summation from 1 to infinity of 1 over n factorial, is that convergent or not? And so we want to figure out what that limit, this limit is. So when we say n plus 1, that means a sub n plus 1. That means we're going to plug n plus 1, that phrase, that expression, we're going to plug n plus 1 into n in our expression. We're going to plug n plus 1 in for n. So they have here 1 over n plus 1 factorial over 1 over n factorial. So they plugged the expression n plus 1 in for n, then put it over 1 over n factorial. And then when we do that, well, we're going to flip multiply that. And so we have n, I should still have my limit notation, limit as n approaches infinity. We have the value of n factorial over n plus 1 factorial. Well, okay, well, how factorials work is it's just taking that number, multiplying every number below it. Meaning, anytime we have this n plus 1 factorial, or if we had n plus 2 factorial or something like that, we can always split things up. Limit is n versus infinity. And what I mean by split it up is I can pull out the n plus 1 times, well, n plus 1 factorial is n plus 1 times n minus 1 times blah, 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 all the way down to 1. So n plus 1 factorial is just n plus 1 times n factorial. We still have n factorial on top. Well, now n factorials cancel. We just have the limit as n approaches infinity of 1 over n plus 1. And we still want to evaluate that limit, figure out what that actually is, and that equals 0. And since it equals 0, it does converge. 0 is less than 1. So if we get any value for our capital L that is less than 1, that series will be absolutely convergent. And if we get some value for our limit that is greater than 1, it will be divergent. If we get exactly 1 inclusive, doesn't tell us anything. So that means that the sum from n equals 1 to infinity of 1 over n factorial is absolutely convergent by ratio test. Okay, let's look at some of these ones down here. Okay, well, we are asked to expand the series and to determine if it's convergent or not. And so again, I'll just write the first 4 terms. 4 to the 0 power, that's 1 over 0 factorial, which is 1, plus 4 to the first power, that's 4 over 1 factorial, which is 1, plus 4 squared, so 16 over 2 factorial, which is 2, then plus 4 to the 4th power, that'll be 64, well, cubed, well, 4 cubed is 64, yeah, over 3 factorial, which is 6, blah, 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 so on and so forth. Okay, so that's what's happening there, and we're now going to compare, well, not compare, make a ratio of 2 consecutive terms. So the limit as n approaches infinity of the n plus first term, so that means we plug n plus 1 in for n. So we have 4 to the n plus 1 over n plus 1 factorial. And we are dividing by the ratio as is, just a sub n. So again, we're doing the limit of a sub n plus 1, plugging n plus 1 in over a sub n, which is just that sequence. One thing, you can just skip this step. This step right here, where we have the fraction divided by that fraction right there. You can go ahead and flip and multiply the bottom fraction. You can go ahead and flip and multiply the bottom fraction. So you don't have to write it like that first when you're doing this. So you can follow your algebra. So I'm going to go ahead and flip and multiply the other fraction, making this now n factorial on top over 4 to the n, 4 to the n on bottom. We're doing that limit. Okay. So just now, just like last time, limit as n approaches infinity This n plus 1 factorial, I'm going to split it up to have n plus 1 times n factorial. We also have 4 to the n power on bottom. We have n factorial on top times. Okay, we have 4 to the n plus 1. Can we split that up as all? In any sort of similar way, have how I split up the n plus 1 factorial?
Four to the n plus 4 to the first, or just 4?
Times 4.
Times.
Times 4.
So we want to remember, if you ever have something that looks like x to the a plus b, that can be rewritten as x to the a times x to the b. And that's essentially what I want to do right now. I'm going to split it up like that so that I have 4 to the n times 4. I mean, I could put to the first power, but that's redundant. And right now, some things can cancel, which is my absolute value. Some things will cancel. We have 4 to the n on top and bottom, so it cancels. Change colors. N factorials cancel. We just have 4, that's just a 4. 4 over n plus 1. Since we just have 4 over n plus 1, I'll rewrite it like that. Limit as n approaches infinity. The absolute value of 4 over n plus 1. Well, that limit is 0. So, converges by ratio test.
Do we just say converges, or do we have to say absolutely converges? Or
So if it doesn't flip sign over and over, absolutely convergent isn't super necessary. And also, if you're asked to show whether it converges or diverges, saying that it converges, whether you have the absolute on there or not, does still answer that question. Because this would absolutely converge, because what happens if I throw an absolute value sign on there? Nothing, right? Because there's no negatives. So the only time you would definitely need to have the word absolutely is if there's negatives involved, to show that it's still going to converge even with the absolute value sign. But having absolute value, absolutely, they wouldn't take off for that. But it's not necessary, because they're really just asking if it converges or not, and that does still answer that question.
okay.
Okay, I'll do. Let me see. Let's see how fast I can do 2 more. So this one, when we start plugging stuff in, we have 4/3 plus 16 over 18 plus 64 over 81 plus 256 over 324. Okay, and it's just going to keep going kind of in that sort of pattern. Now we want to do the limit as n approaches infinity of the absolute value of, okay, a sub n plus 1, so we're going to plug n plus 1 into all of this. So 4 to the n plus 1 power over n plus 1 times 3 to the n plus 1 power. Okay, and like I did on this one, I'm going to go ahead and flip and multiply the other fraction. So then it's going to be times the a sub n expression flipped. So n times 3 to the n over 4 to the n. And that's what we want to figure out. And we'll go through the same process as I did on the last one, splitting some stuff up. Limit as n approaches infinity. So 4 to the n plus 1, that can split up into being 4 to the n times 4. Then we got times n times 3 to the n. All over the bottom, we have n plus 1 times, I'll split this one up too, so that will be 3 to the n times 3, n times 4 to the n. Okay, what things cancel? The 4 to the n's cancel, and the 3 to the n's cancel. We just have the limit as n approaches infinity of 4n over 3 times n plus 1. And that limit is what? 4/3, good job. So, since this limit is bigger than 1, it will diverge. Since this limit is bigger than 1, it will diverge. That's the main difference here between convergence and divergence with ratio test. If the limit we get is less than 1, converges. If the limit we get is bigger than 1, diverges. So 4/3 is bigger than 1, so it diverges. So diverges by ratio test. Okay, I want to show one more problem. I'm going to flip to the next page. Just to number 7, because the answer is awesome. So on number 7, if we go ahead and write a few of the terms, we have 1 plus 1 factorial over 1 to the first power. So that will be 2 over 1, then plus 6 over 4, then plus 24 over 27, then plus 120 over 256, dot, dot, dot. Okay. So now we want to do the limit as n approaches infinity of. Okay, so we're going to plug n plus 1 in for n. So that's going to, n plus 1 plus 1, that's going to make that n plus 2 factorial over n plus 1 to the n plus 1 power. I'm going to go ahead and flip multiply my a sub n expression. So n to the n power on top over n plus 1 factorial on bottom. Okay, and if we start splitting stuff up, we have limit as n approaches infinity of. Okay, so how I'm going to split the n plus 2 factorial up this time is I have n plus 1 factorial on bottom, and the whole purpose of splitting stuff up is that so things can cancel. And so if I split up n plus 2 factorial in such a way that I have an n plus 1 factorial there, then they can cancel. And so that's what we're going to do. I'm just going to pull n plus 2 out of that and multiply it by n plus 1 factorial. And then the other thing on top is still n to the n power. Okay, then on bottom, we still have n plus 1 factorial over there. Then right here, I'm going to do the same thing as before with our exponents, because this is really n plus 1 to the n plus 1 power, which can be, the exponents can be split up, so n plus 1 to the n power times n plus 1. N plus 1 times n plus 1 to the n power. Okay. And now, well, the n plus 1 factorials nicely cancel. Sadly, that's the only thing that does cancel. So we have limit as n plus goes to infinity of n plus 2 over n plus 1 times, we still have n to the n power on top, and then we have n plus 1 to the n power on bottom. Well, I can put that together and write it as n over n plus 1 to the n power. And so that's what we have right here. well, if we ignore that part, we have n plus 2 over n plus 1. As that goes to infinity, that's going to go to 1. So we really just have this going on that we care about. And if you were to take out your calculator and see what this is going to approach as you go off towards positive infinity, it interestingly ends up going towards 1 over e. Well, e is 2.78-ish repeating, so that number is less than 1. So therefore, converges by ratio test. Oops, sorry. Okay, well, that's now the ratio test. Key will go up later today, as well as the next notes and homework packet we're going to do that we will maybe start on Friday, for sure do next Monday and Wednesday. I'm not sure if we will do the root test or not, haven't decided. Root test is not on the AP exam this year, but we definitely will do the last section that's on review and summary. We'll cover the review and summary section on Friday. What else? Any questions?
Is that the last section of the packet that is online right now? It's just the review and
So
summary.
yeah, the current packet you have, we have this section right here, and then the last section of the packet, section 23, is essentially just a review and summary of all the sequences and series, convergence and divergence stuff. So we're for sure going to do section 23 on Friday together. Probably won't do root test because it's won't be necessary this year and it's annoying. And I will post the key to these last sections today, as well as upload the next packet on Taylor polynomials.
Will we need any of that Taylor polynomial stuff for Friday, or are we just going to review?
So we're going to review, and I may do one example and start the idea, as well as there's a very good video on Taylor polynomials at the YouTube channel 3 Blue 1 Brown, which I'm also going to upload the link to that YouTube video because it would do a way better explanation for the first time hearing about it than I could, as well as the visuals that video does. Helped me find
that guy's great.
Yeah, it helped me finally understand it back in the summer. Okay. I'll post some of those things. We won't do much of the next packet Friday, but I want to start that idea so we get the purpose of Taylor polynomials. Okay. Any other questions? This has been recording, and I will post it to my YouTube channel and the link to the video on the calendar. Okay, well, have a good day. See you Friday.
All right, see ya.
Bye.